Hey engineers, and welcome to 2.1 Intro to Statics. We're going to talk about statics, and it's not the electricity kind, it means still, and what that means for forces, what that means for engineers, and how we use statics to determine whether or not structures and things are safe. Let's get started. I just did a Google image search for statics so you could kind of have an idea of what we're dealing with. Statics are, here's a truss, and it shows how much force is on each one of these joints. It's giving you distances. Here's another truss that's loaded with forces and giving you more distances. That's basically what statics is you have forces pulling down, and you've got a cable pulling up and to the left, and you've got a cable pulling to the right. Statics is when things are still. All of the forces are going to be balanced. Here's a three-dimensional statics problem where you've got a cable being supported. So this cable AC is pulling up and to the right. Cable AB is pulling up and to the left. So you've got forces acting on an object. And this is what statics is. Forces kind of acting on an object. If something is static, we call that it's at rest, or the forces add up to zero. Those of you who have gone through physics, you can understand that an object can be moving at constant speed and have the forces equal to zero on it. Just because the forces up and the forces down, the forces left and the forces right are equal to each other doesn't mean it's standing still. It means that it's in a uniform speed. The acceleration is actually equal to zero, is a better way to say it. Newton's first law says this, that objects in motion stay in motion, objects at rest stay at rest, unless acted upon by another force. Newton's second law says, this is back from physics, that F equals ma, that if you have a force on an object, that is equal to the mass times the acceleration of an object. Or, in other words, if you've got a really big mass, it's hard to accelerate you. If you've got a really small mass, it's easy to accelerate you with F equals ma. Newton's third law says that for every action, there's an equal and opposite reaction force. Static equilibrium means that it means that all the forces are equal. Like if there's a downward force of gravity, something has to be pushing you up. If there's a pull towards, I don't know, this is my left. I don't know if it's your left, the way you're looking at it. If something is pulling left, that means that something is also pulling right at the same amount. Static equilibrium means that everything is equal. Up equals down, left equals right, forward equals backwards. And when we get into torques, clockwise torque equals counterclockwise torques. So here's some fancy words. Symbols. This means that you add them all up. Remember how I told you that if there's anything pulling you to the right, maybe something's pulling you to the left at like 10 pounds. You could have two forces, a 2 pound and an 8 pound. You add the 2 and the 8 and they equal. So negative 10 plus 8 plus 2 equals 0. And so you're adding up all the forces in the x direction. Now some can be positive. Some can be negative. The positive and negative just mean the direction that they're pulling. Why? Maybe gravity's pulling down at 100 pounds. So negative 100, and if the ground is supporting you, plus 100 equals 0. You add up all the forces. There can be multiple ones pulling up and down, but you add them all together. That's all this symbol right here means. It's the symbol sigma. You add up all the forces in the x direction, and they should equal 0. Rotational, meaning that if you've got clockwise, so they signify clockwise torque, like all these objects over here are cranking this seesaw clockwise, and that's going to equal the counterclockwise. So this red ball over here is turning this thing counterclockwise. These two torques equal each other. Not the forces, but the torque. The force times the distance. So if this was a 10-pound ball and it's 1 foot, so that'd be 10 times 1, which would be 10 foot-pounds. Maybe this is only like 2 pounds, but this would have to be 5 feet away. So 2 times 5 would equal 10. So the torques are equaling each other. If you add up all of the moments or the torque, so sometimes we have a positive. The blue in this case would be a positive torque, and negative would be, and maybe we switch those around. Remember in math class how when things go around the Cartesian plane in counterclockwise, that's positive. So maybe this red one means positive and the blue one is negative, so then they add up to 0. There are two things in statics, two types of measurements. One is called a scalar and the other one is called a vector. For instance, force. It matters a great deal if I told you I'm pushing you with 100 pounds. Am I pushing down on you or am I pushing you forward? The direction of the push is really important. Like time, there's no time that nobody cares what direction you're moving your watch. Like that time is time. So scalar quantities, things like time or volume or temperature, pressure, speed, they don't matter what direction that they're going. So a scalar quantity only is how big. Like what's the temperature outside? Oh, it's 50 degrees. Doesn't matter what direction. But a vector quantity does. So a force is definitely a vector quantity, and we're going to be dealing with forces all the time through statics. It depends. Are you pushing down or are you pushing forward or are you pushing at an angle? So these are things. Velocity. You saw before there was speed. Speed is to velocity as scalar is to vector. Speed is a scalar. Velocity is a vector. It's funny, they actually have the same letter S. Speed for scalar, V for velocity, for vector. And moment, so torque, it can be a positive or negative, like clockwise or counterclockwise. So it does matter. These two things is why, and that's why they're underlined, because we're going to be using moments and forces quite a bit. What is a force? A force is simply a push or pull. You can push objects, you can pull objects. Gravity pulls things all the time, and that's probably the number one force we're going to be dealing with, is things' weight. You can pull things with ropes. There are beams that we can lift things with, all sorts of things, but a push or a pull on an object is that's what a force is. Now, here's an example, 45-pound force. So LBF, that just means pound force. It's the exact same thing as 45 pounds. But you're pulling 45 pounds at an angle of 21 degrees north of east. So you're pulling up and you're pulling to the right. You're pulling north and you're pulling east simultaneously. And you're applying that force at point A. So units of force, in English we use pounds, but everywhere else in the world they use newtons. 1 pound is equal to 4.4 newtons, or if you've got 1 newton, it's equal to 0.22 pounds. Every action has an equal opposite reaction. So if things are in equilibrium, that means that they have, only when they're in equilibrium. If they're not in equilibrium, one of the red one can be bigger, like rocket ships going up to space. The upward force of thrust has to be bigger than the force of gravity to accelerate you away from Earth. So they don't always have to be equal, but if they are in equilibrium, they are equal. That's what the word equilibrium means, that the red one equals the blue one. The red one, the right, equals the blue one to the left. The clockwise moment equals the counterclockwise moment. So if they are in equilibrium, these are equal. Up equals down, left equals right, clockwise equals counterclockwise. And we're going to use this idea a lot in this chapter. Forces can be broken down, and you saw me do this before when I was back here, that this is pulling up and to the right. We're going to break it down into what are called components. This force, before I think it was like 45 pounds, and this one's pulling up and to the right as well. So here's that force pulling up and to the right. So we're going to break that force into, we're going to simplify it. It's funny, we make it more complicated to make it more simple. But what we're going to do is we're going to take this force and we're going to break it into what we call the y component and the x component. So we use this notation right here, the force at A in the x direction. So this is the force at A in the x direction. This is the force at A in the y direction right here. So we're going to take this original arrow, which you can't see the arrowhead right now, but we're going to break it into its x and its y components. The resultant. When you have a lot of forces pushing on something, we call that the resultant force. For instance, if I'm pushing to the right with 5 and 2, the resultant is 7 pounds to the right. Now, if I'm pushing to the right with 5 and to the left with 2, 5 plus -2 is +3. So I have a resultant of 3 pounds. So this was an introduction. We're at the end of 2.1. And then you're just getting an introduction of what are resultants. You know, the single force that's the added, you add them all up algebraically. We have components of forces, equilibrium, up equals down, left equals right, clockwise equals counterclockwise. Vector quantities, things that have magnitude and direction, which force and moments definitely are. And you got an introduction to this notation here. This is the sigma, remember? And we add up all the forces in the x direction, and they have to be equal to 0. And we're going to add up all the forces in the y direction, and they equal 0. And you're going to see that we add up our moments, and they equal 0. Thanks for hanging out.